bunch of practice problems for you. Most of these, except this one, is very posted on Smart site. So I'm going to start with another one that's also posted. It was just so huge, I couldn't fit it all together. So I'm actually going to start with this one. Okay. These are just balancing examples I've set for you. Some of them you'll need to be able to predict the products classed by the reaction, like the first one. The first one, what type of reaction is this one? It's a single replacement. It's got a lone elemental form, in this case a metal, with an ionic. So it's going to form manganese plus aluminum sulfate. This is what you should get. For this one, make sure you can write that aluminum sulfate out correctly with the correct subscripts, because aluminum is plus 3, sulfates minus 2. Okay, and then we need to balance this. Let me get that overhead out. So we'll balance this. Let's see. 2, 3, and 3. You should do it. And there we go. We're done with that one. Next one, you want to have to write the products in this case, but it's what category? Should say decomposition in this case. Decomposition for the second one. Here you merely need to balance the carbons. So the CO2 over here, looks like we need 3 of them. We'll do it. One's in the other places. Okay, for the next one, what category for this one right here? That will be a double replacement. You have 2 ionic compounds reacting together, so it'll be a double replacement. So we have calcium. What's the name of that first compound? Calcium acetate with potassium phosphate. That's going to make, let's remove the blinders here, calcium phosphate with a potassium acetate. Okay, and then let's balance that. Again, I usually try to start with something that has a bunch of ugly subscripts, say the calcium phosphate, 3 calciums. 3 calciums, 2 phosphates, so 2 phosphates, that makes 6 potassiums and also 6 acetates. There we go. And then the last one, it's not a particular category, nor would you be able to predict the products. I just picked a slightly more difficult one for us to practice. Again, I try to start with the one, I start with the one that has the funniest subscripts, so that would be this potassium sulfur compound, which we would call tetraphosphorus trisulfide. It'd be a molecular compound. Okay, so for those, so I put a 2 here, so I have 4 phosphorus on both sides, just so you see how I talk this out. And then I have 3 sulfurs, so I want to put 3 sulfurs. I can't balance the potassiums because they're unknown on both sides. I can't balance the chlorines yet, but I can try for the oxygens. How many oxygens are in the products right now? You should see 16. 2 times 5 is 10. 3 times 2 is 16. So what do I need right here at this moment? Multiply by 3 to get 16. It better be 16/3. Well, I don't want fractions as my answer, so I'm going to multiply through everything by 3. So 3, this will become 16, this will become 6, 3, and 9. That would be my final answer. Sulfur and those products in combination, when you light a match and you get that characteristic match smell, that's this reaction. Okay, you might be thinking, wow, that was way too easy. Let's do a harder balancing one. Cool. I brought one for us. This is, I would consider this a pretty difficult balancing one. Could take you, upwards of, 5-10 minutes easily. Here's how I would approach this one, just so you can see my style. So I would say, okay, this one looks the worst as far as subscripts, this first compound there. So that's probably where I would start. And I would say, well, there's 5 calciums there, and there's 3 calciums here. So let's make 15 as the lowest common multiple, 3 and 5. Let's start that way, as far as the balancing goes. And then, my next step, let's see. The phosphorus, I guess I could try to tackle. Phosphorus only lands on 2, but it's all by itself. It doesn't really progress me any, but if I wanted to, I could put, how many phosphorus are right here in the reactants right now? There's how many? 9, yeah, 3 times 3 is 9. So that doesn't really get me anywhere. I think the fluorines, though, can help me a little bit. The oxygens would be too hard, but the fluorines can kind of get me somewhere. I have 3 fluorines here, and I have 4 here. So I could put a 3/4 here, but that's going to start to get a little messy. So I'm just going to change pen color now and say, if I multiply these two by 4 to get a 12 here and a 20 here, now notice what happens. I have 12 fluorines there, and I can put a 3 right there. So it allows me not to use, I don't have to use fractions because of that fluorine. Okay, so I got the fluorine handled. Let's go to the silicons. How many silicons are in the products right now? Well, 3 here, and then there's 2 there, times 20, that's 40. 43. Now this is getting awesome. 43 sulfurs there. Okay, now let's see what I would tackle next. I guess I can just, now it's just kind of lone, almost lone elements except for carbon monoxide. So let's do the phosphorus now. How many should I put right here? Yeah, there's 36 from here. 3 times 12. So I'm going to put 36 right there. Okay, I can't do the carbons because they're unknown on both. But I, unfortunately, now have to tackle the oxygens. Okay, here we go. How many oxygens are right there? 86. Okay, how many are right here? Yeah, 12 times 12, 144 plus 86 is? I think 230, right? Okay, so there's 230 oxygens in the reactants. Love this problem. Okay, so let me just make a note. Reactants have 230 oxygens. Atoms. Okay, let's do the products right now as it stands, not including the CO. Okay, how many oxygens are right in here? I got 140. Okay, let's try that together. There's 4 here. Is that okay? 2 times 2, there's 4 right there. Plus another 3. So a total of 7 in this whole complex right there. Okay, total of 7. 7 times 20, 140. So right now, I've got 140 oxygens in the products. Huh? Oh, yeah, she's saying the CO, that's what I'm trying to figure out, so I'm not counting that one yet, it's my unknown. Okay, so thus, going right where you're at right now, the CO, what's my coefficient in front of CO to make this number balance? 90. goodness, the joy sets in. 90 now, so now I'll have 230 oxygens on each side. So thus I need a 90 right there in front of that carbon. Now it's balanced. Together it only took us about 2 minutes. Easy. Okay, so I would consider this a pretty tough one. I just wanted to do one of these so you can see how I would process through it. Okay, let's do this one next. Here, notice here I have a reaction. I'll have to balance it eventually, but I'll have to write it first. But I'm giving you a bunch of information about that reaction. And so in this case, this is a stoichiometry type problem. Okay? I'm giving you information about one, and I'm asking you about, in this case, the mass of hydrogen gas produced. So this will be a stoichiometry type problem. Whenever you get stoichiometry, or anything else that has a reaction, I recommend you write the reaction out. Okay, so let me move this out of the way now. Okay, how's this one work? Well, we've got aluminum foil. So, aluminum, solid, reacts with HCl aqueous. Oh, what kind of reaction is this? It's a single replacement, a lone element plus, it's aqueous acid. It happens to be a strong acid, as you'll learn in chapter 5 soon enough. So this fits for a single replacement. So I'm going to have aluminum chloride, AlCl3, plus what? Yeah, hydrogen does not exist by itself. It's one of those diatomics, H2. And it tells us it's a gas. You don't have to worry about the state symbol of aluminum chloride. So if you didn't know, I'll be pointing it out at other times as well. You should know the diatomic. So hydrogen is a diatomic H2. Then there's N2, O2, F2, that whole part of the row right there. And then the whole halogen column. Fluorine 2, chlorine 2, bromine 2, iodine 2. All those are what we call diatomics. And in elemental form, they exist with 2 together. Okay, so make sure, that'd be a common mistake when people write out this kind of reaction. Now let's write out what's given. I'll do that in a different color pen. Aluminum foil, and that's an excess, so don't give us information about that. But it's 225 milliliters, and it's 1.088 grams per milliliter. And there's 18% HCl by mass, and then we want to know the mass of hydrogen gas produced. Okay, this information looks a little weird, but when it comes in that combination, there's only really one way to deal with it, and that is to use this information to find the mass of HCl, and then when you get to mass, you can continue to go to moles. So let me show you how I would do this. I get a different color pen now. I would start off with a 225 milliliters. Okay, and that's of HCl. This is HCl. Okay. Let's see. Yeah. Now what I'm going to do is multiply by the density, 1.088 grams per milliliter. Okay? And that's our solution density of HCl. And then what I'm going to do, whenever you have that percent by mass, working backwards, which we haven't done before. So here's what it would look like to work backwards from a percent mass. What that means is 18 grams per 100 grams. Or more specifically, this is 18 grams of HCl in the aqueous solution total. So for every 100 grams of solution, 18 of it is HCl. The rest would be water. So that means 100 minus 18, or 82 grams would be water. Okay, so that's what that means. Okay, let's do a little canceling before we continue on. So this is our HCl solution here, which cancels with the milliliters of that solution. This is the mass of that solution, which cancels here. This is the solution density. And now we're left with grams of HCl. Now that I have grams of HCl, I can work with that to go to moles. So whenever we're doing a stoichiometry problem, I need to convert this mass, whatever I'm given, to moles. So I'm finally able, after all that conversion, now to go to moles. Using the periodic table, it's 36.46 grams per mole, and that's of HCl. So notice now, the grams will also cancel. Finally, I'm at moles of HCl. Okay, in order to continue with my multiplication, I need to do something I haven't done yet. I need to balance the reaction. So let's balance the reaction. Compared to the other ones, this should be baby stuff here. Okay, so you got your reaction balanced. I'm going to continue my multiplication now. I'm at moles of HCl, so I'm going to continue on the next line here, times. Okay, I don't need moles of HCl, I need moles of H2. There's 3 moles of H2 for every 6 moles of HCl. There's my molar ratio from the reaction after having balanced it. And now, my last step in stoichiometry after I do my molar ratio is to go to the unit requested, in this case, mass. And so it's 2.016 grams per mole of H2 from the periodic table. That'll get me to grams. Everything now has canceled. I've lost the moles of HCl. I've canceled the moles of H2. I'm left with grams of H2, which in this case is 1.21. How many Sig Figs do I want here? Yeah, I should be looking at 3, so it's 1.22 grams of H2 is my final answer. I wanted 3 Sig Figs because the smallest amount of Sig Figs in the question was 3 with the 225 milliliters. All right, any questions on this one? I know for some of you it might be the first time seeing how to work with density. This is pretty typical where you're given a volume, you're given a density, and you're given a percent by mass. Those are all multiplied together. Okay, that's how that works. Okay, I'm going to continue on to the next example. We've got some exciting examples here. Let's do this one, the baking soda one. Oh, yeah. So this is kind of the situation where you are at, a ball game, the Giants or whatever, and you have baked 3 or 4 hot dogs. And your stomach tells you should have 1 less hot dog, and you've got the rumbly tumblies in your stomach, and you need some antacid. You have access to milk of magnesia, and you have access to the baking soda, both to neutralize your stomach acid. And you're wondering, oh no, I have both. One friend offers you each. You're wondering, which one should I use? You're like, quick, somebody, give me a piece of paper and a pencil. Let me do a quick calculation. Because I want the one that's more effective at neutralizing my stomach acid. And we're assuming our stomach acid is in the form of HCl, which is a fine assumption. So here's how we'll do this. First, these are both reactions. Let's write out our reactions. In one case, I have baking soda, which I told you last time is sodium hydrogen carbonate. That's baking soda, sodium hydrogen carbonate. We're going to react this with HCl. Again, what kind of reaction is this? It's a double replacement. So I'm going to get NaCl and H2CO3. This H2CO3 actually does another reaction, which you'll learn in chapter 5, but I won't cover it here. And then I'm going to leave a little space for my calculation. I'm going to write down the second reaction down below. The other reaction would be magnesium hydroxide, that's milk of magnesia, that plus HCl. What kind of reaction is this? This is also a double replacement. Two ionic compounds and the aqueous acid, a strong acid counts as well in the double replacement. So we'll get MgCl2 and we'll get HOH, which I would call water. Okay? We get HOH. And now let's make sure that this is all balanced and stuff like that, and we're happy. Sodiums look good. I think this one's pretty well balanced. Let's look down here. I think we need 2 waters, and we need 2 of those. And that should do it. Okay. Now let's do, now that we have, remember those 2 reactions, because I'm choosing between 2 antacids to react with my stomach acid, which is right here. The HCl is the stomach acid. Okay? So our calculation now. Let's do the top one. So let's say I started with, like it says in the question, 1 gram of each antacid. What I'm trying to figure out is how much HCl will be neutralized. So I'm calculating in both cases the amount of HCl. So in the top case, first let's convert to moles. We're doing stoichiometry. Y'all just convert to moles. And I already calculated the molar mass. It's 84.01 grams per mole. That gets the moles of the baking soda, which is sodium hydrogen carbonate or sodium bicarbonate. And then there's 1 mole, and we're going to moles of HCl. For 1 mole of HCl for every 1 mole of baking soda, NaHCO3. I could go to mass here, but I don't have to. I just want an amount, and moles will be fine. In this case, this will neutralize 1.19 times 10 to the minus 2 moles of HCl. Okay, that's how much the first, that's how much the baking soda will neutralize. Now let's try the milk of magnesia. Okay. In this case, we're going to do the same thing, starting with 1 gram of the reactant, MgOH2, magnesium hydroxide. In the same way, convert that to moles. Just like we always do, go to moles first, 58.32 grams per mole from the periodic table for magnesium hydroxide. And then now our molar ratio is a little different for this one. It's 2 moles of HCl, because there's a 2 in front of the HCl, per 1 mole of MgOH2. So this will give me moles of HCl just like above. This is 3.42 times 10 to the minus 2 moles of HCl. Okay. In this case, which one would I prefer to take? The baking soda or the milk of magnesia? I would take the second one, the milk of magnesia, because it neutralizes about 3 times more stomach acid than the first one. Okay? 3 times more stomach acid, given that each friend offers you an equal amount of the starting material. So I would use this one right here. 3 times more effective at neutralizing stomach acid. Alright, that one cool? Okay. Let's try this one. This is the one I did not have on Smart Site. Just oversight, I forgot to put it on there. But this is a really typical calculation. That's why I wanted to do it with you. Pretty standard, typical calculation that you can see. It can be confusing the first time you see it, but once you get used to it, it follows the same procedure all the time. And it looks a little bit similar to that aluminum foil example we did. In this case, you see 1 compound sodium hydroxide. We're given a couple pieces of information about it, and we want the molarity. So if you have 1 compound, and that's it, there's no molarity change, there's no volume change, there's no reaction, then this is purely a unit conversion. We're just going to convert units. This is one of the 3 types of molarity problems I talked about before. Okay, let's try this one, and you'll get used to how it works here. I can start with a number of different, either of these pieces of information. I'm going to start though with a percent, and this is a percent by mass. So just like in the last example, it means there's 50 grams, and I'll write this out, of sodium hydroxide per every 100 grams of solution. So if there's 50 grams of sodium hydroxide, what's the other 50 grams? Water. We're not going to need that in this particular example, but just so you know, it's sodium hydroxide and water makes up the solution. Okay, now we're given a solution density. Here's how you use that. Remember, for molarity, I'll write this down here. Molarity is moles per liter. And it's liter of solution, specifically, and moles of solute. And our solute is going to be sodium hydroxide. So I need to get to these units. Those are my final and desired units. So first, let me work on the denominator, liters of solution. Okay? So I'm going to work on liters of solution. All right, how do I do that? I'm going to use the solution density to do that, 1.5290 grams, and this is of solution per milliliter of solution. So typically when we give you a density, even if it's not labeled, we're talking about solution density. Notice what this does. It cancels out my grams of solution in the denominator of the first number. Then I can do one more simple step to say, well, there's 1,000 milliliters per liter. And now, getting rid of the milliliters, I now have my desired unit in the bottom, in the denominator, liters of solution. So I've got half of it done. I've got the denominator done. Now let's work on the numerator. Right now the numerator is grams of sodium hydroxide. I don't want grams, I want moles. So this is going to be a one-step for this part. We'll say, well, using the periodic table, there are 39.997 grams per mole of, oh, there's not H, sodium hydroxide, NaOH. So that's just from the periodic table. Notice that cancels the grams of sodium hydroxide, and I'm left now with moles of sodium hydroxide. I have my molarity units, and this turns out to be 19.1 molar, my final answer, where molar is moles per liter. Again, pretty typical example for a unit conversion problem. You just need to get used to doing this time. So I worked with the denominator first, and then the numerator second. You could have gone in reverse order, that would have been totally fine. Any questions? Okay. Cool, let's see what we got next. Our schedule. Okay, let's see. Check. We're in chapter 4. We might even finish chapter 4 today. We'll do a little bit of chapter 5. We'll see. What else was I going to tell you? It's almost time to start thinking about exam 1. It's about a week and a half away. So doing practice exam is a great way to practice. What I'll do also, if I haven't posted, I'll usually post the 2 most current practice exams, and I'll put their statistics with it so you kind of know how to grade yourself. I would do the blank first, and then, or cover up the answers, do that first, and then grade yourself. And you can compare with the statistics I'll put up how well you're going to do. So for example, if you're always getting a mean, you're probably going to get a high C. Okay, so if you keep doing practice exams, you get the mean, that's a high C, and that's most likely what you're going to get on our exam. Okay, given no outside other issues. Now, what else was I going to talk about? Oh, I have a couple announcements for you. Here we go. This week, because of a meeting that came up, I'm not going to have office hours, unfortunately. But you can always go. My TAs will have office hours just downstairs at 1064. So I'll alert them that some of you are coming during this period. Chunyi and Patrick have office hours in this time period. So if you have any questions, they'd be great people to ask. That's one announcement. So no office hours this week in particular. That will resume next week. The other thing I was going to tell you, yeah, just one. Sometimes I do events outside of chemistry that I like to tell you about. This one happens to be on campus. I'm going to this event called Knockout Slavery, which is about, fighting against sex trafficking in the world. And one thing that's the way they're doing it is knockout, because they're going to play knockout, and the funds raised will go to efforts to uncover and rescue trafficked slaves. And that's going to be in the pavilion, so I'm signed up to play knockout and hopefully beat a bunch of people. So if you want to come, feel free. I bought some extra flyers. I'll put up here. Okay. And what else was I going to tell you? Oh, occasionally in the reader, there's mistakes, because I'm only human, surprise. Like, for example, on page 29, on the middle of the page, limiting reaction controls the true amount of C4. So what I was going to tell you about that, if you find a mistake before I do, or before one of your buddies in the class does, you can send it to me, and if you send me a few, then at the end of the quarter I'll give you extra points. Okay? You can't just find one, you got to find a few of them. But if you find some mistakes, whether grammar or numerical, you can send it to me via email. And I'll give you a little bit of extra credit at the end of the quarter. Okay. Oh, and one more thing. I know I have a lot of announcements today. And then we'll go to section 4. Feel free to, if you see me, to say hi. I might not recognize you, because there's quite a few of you. You can say hi and reintroduce yourself. It's hard for me to remember your names. If you introduce yourself a couple times, I'll eventually remember. I saw, and the reason it made me think, I thought of that, to say that, I was in Irvine this weekend, and I saw somebody, or they saw me. So it's really random places I see people sometimes. Some people in SF, I've seen students in Disneyland one time, Lake Tahoe, all random places you guys are following me around. So, which is fine, you can, I guess. Don't be a creeper though. Okay. We're in section 4, which is page 29 of the reader and page 131 of the textbook. Okay, let's do this section 4. Limiting, abbreviate LIM, limiting reactants, also called limiting reagents. Both are the same thing. Limiting reactants or limiting reagents, same deal. Let me show you a picture. Oh, yeah. I guess I'll draw a picture first. Let's say in your dorms, there are some beautiful boys, beautiful girls. Okay. All right. Each female only has 2 pieces of hair, and for argument's sake, for your dorm, let's say only males like females. If you want to do a different iteration later when you get home with your buddies, please do so. But for simplicity, I'm going to say males like females in this case. So, in your dorm, there's 4 people, and of course, each of them date. What else would they do? Unfortunately, she dies. Sorry, it happens. So now, you're left with this, and this female is now called the limiting reactant. And these boys are called in excess. She gets to wait for both of her suitors to woo her. She gets to choose who's giving me the best dowry or whatever. Okay? So this situation scenario also happens in chemistry. Okay. In the top case, the larger spheres are iron. In both cases, larger spheres are iron, the smaller spheres are sulfur, and they're reacting to form iron 2 sulfide, or ferrous sulfide. Okay? You can see in the top case, what's the limiting reactant? Iron. There's less iron, so there's extra sulfur left over. In the bottom case, what is in excess? Iron's in excess in the bottom, there's too much of it, sulfur is the limiting reactant. Okay? So this is a concept that we can actually do math with, and we will, in just a moment, as soon as I turn the page. Okay, cool. Let me tell you about these problems a little bit first. So in these kind of problems, there's a couple things to know. Okay, limiting reactant problems. Here's the key first. The key is looking for something that's called over-specified in math. Over-specified. What does that mean? If I write out a reaction, A plus B goes to C plus D, let's say we want to know about this one. Okay? We either want to know about mass or moles. Either one. Mass or moles. And let's say mass of this one is given and mass of this one is given. It could be moles too. It doesn't matter. It's an amount. Okay, now look what happens. If I want to know C, I can do a stoichiometry problem with A, converting it to moles, doing a molar ratio, and finding C. Or I could use B, convert this to moles, use molar ratio, and then convert to mass or moles of C. So now there are two pathways to the answer. I have too many knowns and not enough unknowns. So that's what we call over-specified. Now mathematically we wouldn't be able to choose between the right answer, but chemically we can. We're going to do here two stoichiometry problems. So it's stoichiometry, but double. So if you really like stoichiometry, now you get to do it twice as much, and it's that much more fun. And you're just going to go through it twice. And basically, after you do that, you're going to, I'll put a little bullet here, find mass or moles of C, mass or moles of C. And then smallest answer is from the limiting reactant or reagent. Okay, so the smallest answer is from the limiting reactant. The larger answer is from the one in excess. So that's how chemically we'll determine. Basically, one of these is going to run out first chemically, and that one will control the amount of product made. Let's do a simple example. This is the Haber process. I think I've had this reaction for us already. It's balanced. It's forming ammonia. Now let's say if there was 2 moles of this and 3 moles of this, how much product will I form? I'm going to form 2 moles because what's the limiting reactant? This is limiting. How much of this will I use? I only need 1 to 3. I have 2 to 3. You see that? But I only need 1, so 1 mole unused. So nitrogen is in excess. The hydrogen is limiting. And so I'm going to end up forming only 2 moles. Now if I had a total of 6 moles of H2, I can form more ammonia. I can form 4 moles. I only have 3 moles, so it's limiting the amount of ammonia I can form. So this is a simple one you can do in your head. We're going to do some more exciting stuff that we get to use our calculator, because I know you like your calculator. You have a special relationship with it. I'll put that up, and we're also going to take a break. We're going to do this problem. I have a demo. I have this Tesla coil here. It creates a very high voltage at the tip of this, and it arcs into the air. And I need that because I brought what we call, in our department, an ethanol can. Here's our cannon. It's a 6-round shooter. Each one of these are identical. And, I autographed each of them. Now in here, if you take a look, if you can see there, those 2 nails, they're not touching, but they form a little gap where it can spark. And I have in there, you can see maybe a little bit of liquid. That's ethane. And so that's going to undergo, there's oxygen in here too. I had this open earlier. Oxygen plus ethanol, what kind of reaction is that? Combustion will form CO2 and water. As gases, there will be an expansion. And a lot of bombs work that way. It forms a gas, which is an expansion, and it'll push the cork out. Okay? Cool. Awesome. I know exactly what I'm going to shoot too. The person who teaches the previous class, I'm on a committee with, we're on the safety committee. He was like, what are you doing shooting students? I'm assisting on the safety committee. Oh, well, some people I've been wanting to shoot. Now, well, I did the lights because you might be able to see a little bit of fire trail with it. It kind of depends on the angle where your seat is. Don't worry, you won't catch on fire. I'm going to hold this close to my mic, and maybe you can hear the sound of the arcing in the air, okay?
What?
Can you hear that at all? A little bit? It's like a buzzing sound, essentially. And if you could see it, I can actually see it arcing into the air, those little blue arcs. Okay, unfortunately I didn't have a lot of ethanol to put into here, but hopefully it's enough that some of the 6 at least go off. We'll give it a try, okay? Alright, let's see which fools. Okay. Oh yeah, I'm serious. Oh, there we go, there's one. This last one, this doesn't want to go. Okay, cool. Here, you can have that. Alright. Not bad, huh? You guys like that demo? That's combustion. So much gas going on, just like your car. The spark plug, it has a small gap that you can actually measure and adjust, and that allows for the spark. Combustion happens, and thus pushing the pistons out, and then coming back in, and that's the reaction. Okay, so cool. Love that. You can keep the forks, by the way. Show your little cousin when you get home. Okay. If you're rich and famous, you can invite me to your resorts and pay me. Okay. All right, let's try this. There's 2 questions. One I have written in pen. We're going to do the second question in a minute, but we're going to focus on the type part here right now. Let's write out the reaction. 3, manganese 4 oxide. That would be, MnO2. Leave room, we're going to balance in a second. Plus liquid aluminum. This is what kind of reaction? Single replacement. We have a lone element and an ionic, so we're going to form aluminum oxide, Al2O3, plus lone manganese. We want to balance this. There's a 3, a 4 aluminum, 3 manganese, and 2 aluminum oxides. We'll do it. And now let's write down the information we have underneath. 50 grams of this. We have 25 grams of aluminum. And how much liquid manganese is produced? So we want to mass. Okay, this is a stereotypical limiting reactant problem. The reason I know that is information is given about more than one reactant. Okay? Because I have information leading to moles of more than one reactant, it's overspecified. Because it's overspecified, it's a limiting reactant problem, and I have to do 2 stoichiometry problems to solve this. And I'm going to use both of these to find the mass. So literally 2 parallel problems here. Let's first start with the manganese oxide. It doesn't matter which one we start with. Okay, 50 grams of the manganese oxide, manganese 4 oxide. Change that to moles. So stoichiometry, go to moles first. From the periodic table, 86.94 grams of manganese oxide. Now convert to moles, 3 moles, or mole ratio of manganese, and 3 moles of MnO2. So first step, go to moles of manganese oxide. Second step, molar ratio. Third step, go to what was asked for. Okay, that's the mass of manganese oxide. Using the periodic table, 54.94 grams per mole. 31.6 grams of manganese. Okay, we did one. Now I'm going to get a different color pen out and do the other one identically to what I just did. And I'm going to do this for aluminum. Okay, my other reagent that has information leading to moles. This is 25 grams. I use first convert that to moles. From the periodic table is 26.98 grams per mole of aluminum. So I have moles of aluminum. Now I'm going to use a molar ratio. Go into manganese again, 3 moles of manganese, same numerator, denominator is different, there's 4 moles of aluminum now. Canceling out aluminum. Now, same last step, I've got to go to grams. So it's 54.94 grams per mole, same number. This turns out to be 38.1 grams of manganese. Again, I found the same thing, but from different starting points. Now I'm going to get a different color. Okay, which one's the correct answer, top or bottom? Top, the smaller answer is the correct answer. It's right there. Why? Because it gives the least amount. The limiting reactant constricted it. The second one assumed that we had more manganese. So the limiting reactant is this. The manganese oxide. This is the limiting reactant. What do we call aluminum? In excess. Aluminum is in excess. There's too much of it. Okay? And so 31.6 is the answer you report. Okay, any questions on that? All right, now I'm going to turn your attention to page 30 of the reader, if you have that with you. I'm going to show you that in my handwriting. But a common question to ask, before I go on, a lot of you are going to ask, so I hope you're listening now, hey, can I solve this a different way? Yes, outside of cheating, if you want to solve it a different way, that's fine. You can do that on the test, just make sure it's clear. All right, now, this second question is a very common question. What mass of excess reactant remains after the reaction is complete? We started with, remember, aluminum is 25, that's in excess. What does that mean? I did not use all 25 grams of aluminum. I used less, maybe 5 grams, maybe 20 grams, whatever. I used less than 25 of the aluminum, okay? So I want to know how much is left over. Because if you're, in the industry, you want to know how much extra material you have that you can reuse it later. So how do you find the mass of a reactant in excess? How do you do that? This is the flow that I do. Again, there could be different ways of solving this. That's fine. Outside of cheating or doing something ridiculous, it's no problem. Okay. So start with your limiting reactant answer. For us, that'll be the 31.6. We'll do this in a minute. You're going to convert that to moles if it's not in moles already. Then what you're going to do is you're going to find the moles of the reactant in excess. So you're going to go from moles of the answer, which in our case is manganese, to moles of aluminum. So you're going to calculate the moles of aluminum from the correct answer. Then what are you going to do? Once you have the moles of the correct answer, you're going to find the mass of that answer. And so now I have a mass, and it better be less than the amount given. So for us, we're expecting a number less than 25, because that's what was given in the question. And then you're going to use this formula accordingly. The amount given, in our case 25 of the amount of the excess, so aluminum, is equals to the amount remaining plus the amount calculated. So what we have here, the given amount, 25, that's in from the question. We're going to calculate this following this flow chart right here. And so we can find the amount remaining just by subtraction. And that's how much we're going to have left over. Then we can recycle back into the problem, or into the tank, or whatever industrial process we're working with. So this is going to be our flow chart to help us answer how much reactant we have in excess. So we're going to do this exact flow, and this is all written down on the top of page 30 of your reader. We're going to do this for our problem. Let's do that. So again, how much aluminum is remaining after the reaction is complete? Here's what we do. We take the 31.6 grams of manganese, the correct answer, we start there. Change this to moles. So I'm going to redo one of those calculations I just did, using the 54.94 grams. Now I have moles of manganese. Now, unlike this problem here, I'm not going to go to MnO2, I'm going to go to aluminum, the one in excess. So this is like the third bubble here in our flow chart. Find the moles of the reactant in excess, that's aluminum. So use our molar ratio. There's 4 moles of aluminum for every 3 moles of manganese. And you'll see the moles of manganese will cancel. Now I have moles of aluminum, but to do the problem I need mass. So there's 26.98 grams per mole from the periodic table for aluminum. And this gets me, I'm going to write a couple digits down right now, 20.691 grams of aluminum. Okay, let's think about this number first. Is this what the kind of number we expected? Yeah, because less than 25. So we're cool with that. That's how much aluminum actually reacted. Not 25, but 20.6 blah, blah, blah. That's how much reacted. So you can see we're going to have about 4 grams left over. All right, here's the annoying part. Sig Figs. How many Sig Figs does this have right now? Well, I mean, that's how many digits it has, but how many Sig Figs should it have based on the calculation? 3. So let me underline those. Okay. Those are the actual Sig Figs. I know I wrote more digits. Okay, so what we're going to do now is take the amount given, that's the total amount we had, minus the amount that I used. So this is given, and this is used or calculated, and I'm about to find the remaining. Okay, how much remains afterwards? And if you just simply do this calculation, you get 4.309, but we need to figure out the Sig Figs, so let's do that. It's 25.03 there, and then 20.63 here. So, if you line it up, it only goes to the tenths place. So only 2 for your answer, 4.3. So I need to round accordingly. It just rounds to 4.3 grams of aluminum remaining after the reaction is complete. Okay. Any questions, whether it be a Sig Figs or how I did the calculation? Usually follows the same flow, so just get used to it, and it should be fine. Okay, we're going to go to page 30 of the reader. I guess it's the same page. And page 134 of the textbook for the next section, which is kind of a short section. This is section 5, 4.5, other stuff. That did not fit into the other section, so now we have another section. Okay. There's a couple things, additional things that I wanted to teach you here, and I want to cover percent yield. This is the calculating how much did you actually make of something. And you'll do this sometimes in lab. It's the actual over the theoretical and times 100 to make it a percent. What does that mean? How much did you actually make in the lab divided by theoretically, that's the calculated amount, how much your calculator told you you would get. So the calculated amount goes in the denominator on the bottom, and the actual amount, or for us, because we're not in lab right now, actual is the amount given in the problem. So the amount given in the problem divided by what you calculated times 100%. What's the biggest this number could chemically be? 100. What's the smallest this number could possibly be? 0. If you are outside this range, you are crazy. Okay? That's not possible. There could have been a side reaction or something like that, byproduct, something unreacted. All kinds of things would make this. Maybe you'll get a number not in that range, but there's reasons why. So, for example, let's see. We did last time, found, I don't know if you remember the silver bromide problem we did last time, and I think the answer was 2.1 grams of silver bromide. That was the answer we obtained from our calculator. But let's say in lab, there was 1.05 grams of silver bromide produced. So for some reason in lab, you only made this much. So the percent yield is simply 100 times what you got in lab, or what's given in the question, divided by what you calculated from the numbers in the question. And in this case, it's about 50% is what I got. Okay? So what we'll do sometimes to kind of mess with your mind, we'll give you the whole question, just say like we did in the silver bromide, and we'll give you the answer. We'll say 1.05 grams of silver bromide is produced, and we'll ask you how much silver bromide is produced. What we mean by that is when we give you what seems like the answer, that's actually the lab, the actual amount. We still want you to calculate this number, and then we'll have you calculate, say, the percent yield. So this kind of problem goes with any stoichiometry problem, or now any molarity stoichiometry problem, or any limiting reactant problem. Could have a percent yield tacked onto it very easily. Okay, there's one more other. Okay, that's the first other, percent yield. There's one more other in this section. And that's called consecutive or simultaneous reactions. Okay? What is it? This is a series of reactions that occur that will add up to an overall reaction. For example, let's say we have A plus B goes to C. And we have a second reaction, C goes to E. Well, if you add these reactions up, hopefully you notice that the C cancels. So we're left with a final reaction that looks like this. A plus B goes to E. These are called the consecutive reactions, or simultaneous. but we're going to use both interchangeably, consecutive reactions. This is called the overall reaction. And then C, the one that cancels, is called the intermediate. An intermediate is something that appears in the consecutive reactions, but doesn't appear in the overall reaction. Well, another way of saying that, there's no net rate of formation of C in this case. So what's our solving method? For consecutive reactions. I have two steps, two bullets. First, one thing I try to do is cancel intermediates. So find the intermediate and cancel it. How do you find the intermediate? It's whatever's not in the overall reaction. Make sure it cancels. So what you have to do sometimes is flip reactions. You have to multiply reaction by a coefficient like 2 or 7, or things like that to cause those intermediates to cancel. The other thing I try to do is match species or compounds. Oh, that says math though. Match species in overall reaction with W slashers with those in consecutive reactions. So for example, in what we did above, notice in the overall, I need E in the product. E is in the products in overall. That means I need to make sure that this second reaction has the E in the products. So I need to match the E here, which is the correct answer, with the E here, the one that can be manipulated. So these consecutive reactions can be flopped around, multiplied, manipulated in different ways mathematically in order that you add to the overall. Okay, let me say two side notes about this. Oh, and I'll toss these up here. A lot of practice examples. Consecutive reaction, or simultaneous reactions, 1, 2, 3, limiting reactant and yield, all kinds of fun stuff. Some instructors don't overtly teach consecutive reactions, which you can kind of get away with in 2A, because you see it in chapter 5, and when we do redox, those you solve via this method, but they're relatively easy problems. They can get a lot harder, but you're going to see these pretty heavily in 2B and 2C. The problem is, a lot of the 2B and 2C instructors don't teach this either, assuming you got it in 2A. So that's why I'm teaching it now. Some of the other 2A instructors may not teach it, if you're comparing notes with your other buddies. But I just wanted to at least kind of teach it. We'll do some examples next lecture, not right now, so that you can see how to do it, or just look on some of these. These can get pretty difficult sometimes. They're kind of like little puzzles to figure out. So I just wanted to let you know, sometimes they're really easy, sometimes they're hard. And we're going to do a medium difficult one at the next lecture. But if you want to see examples before that, please take a look at your at the YouTube videos. All right. I also wanted to point out on page 31, if you want to see other videos, here's some example exam reviews. I haven't scheduled my exam review yet, but it'll potentially be next Sunday night, if I can get it. I'll announce that at lecture.